And all right, we are on lecture 10, and we're going to cover a few basic things around the edges. We're going to talk about something called global variables, explain what they are and kind of why they're bad. They're not always bad, like any kind of rule. Once you understand the rules, you can kind of understand when you can break them, when you can't. But when we start out as beginning programmers, we try to avoid creating these variables that are kind of omnipresent everywhere. So that's what we are referring to by global variables there. We'll also learn about a new kind of data type in C++ called vector. And it's a basic kind of collection of anything, collection of numbers, collection of letters, collection of words. It really is the workhorse of C++. And it's our first real data structure. It's a structure that holds data. So we call those data structures. You could think of a word as a data structure. It's got a collection of letters. So in that sense, we've kind of been working with a small data structure, but this is our first real kind of workhorse data structure, and we'll use it for quite a few things in this class at least. But many, many people use it in C++. So we'll have a lab today, in addition to our palindrome lab, just a really simple lab, how we write a function that can deal with this particular data type. So far, the things that we've been sending into a function as arguments might be a number or a letter or an entire word. Now we're going to send in entire collections of things like numbers or collections of words. And this is something we'll do for the rest of the semester. So this is a very important data structure. We kind of want to get our bearings on that. Now, easier side of the street, clock for a day, got about a week and a half on that. So not due on Tuesday, but the following Tuesday, that will be due. It's just a for loop kind of thing. It's in a function, a little bit of logic there. Lots of different ways to do this. Everybody approaches it from a slightly different perspective. But if you read the instructions on that, I think you'll find that pretty self-explanatory. And then, of course, our quiz 3. I'm going to slowly start ramping up the essay questions on these quizzes. So I'll try to be conscious of how long these things are taking everybody. Currently, they're all still basically 45 minutes long, but you will need to write, a few more lines of code from scratch in some of these quizzes, and that will get you kind of ready for the midterm, which is really not that far away. We're on lecture 11 today, or 10 today, and by the time we get to 15, we are ready for our midterm. So lecture 16 is essentially our midterm. So that kind of lets you know where we are in the sequence of things. So for today, quick review, little hint on clock for a day. If you haven't started it, I'll just give you a quick couple of suggestions. But like I said, there's many ways to do this. We'll talk about global variables. We'll talk about this vector type, vectors. It's a collection of anything. And we're going to introduce this weird syntax that is referred to as a template in C++. It's sort of a type inside of a type. And it's something you see a lot. You'll see, more and more as we go forward. But the idea with vectors is they're kind of like these magnetic trains. They sort of start out with nothing, and we sort of glue them together or add things to the back of the train as we grow the collection of items. So it's sort of size 0 by default, if you will, and then depending on what we put in it, it might grow and grow and grow. So in that sense, it's a dynamic data structure. We can shrink it or grow it, which is really helpful. Not all data structures are like that. And it has this funny less than, greater than thing we call a template. So it is just really saying, hey, what kinds of things are we collecting on the train? In this case, we're collecting integers on the train. It could be letters, which seems strangely like a string. You might say, well, what's the difference between a collection of letters in a vector and a string? Well, really, it's pretty much the same thing, but vectors are more general purpose. So we could kind of go either path unless, we want to start collecting things like Boolean values or doubles or anything like that. So vector initialization is something also we want to do. Sometimes you want to start out with a set of numbers like we see here, 3, 2, 4. That's just the beginning. And then we might add to it. Or we might start out empty. So we'll look at the different ways of sort of filling up a vector as our program starts so that we have something to begin with. And then we'll write some of those functions, and that should get us to lab pretty quickly. Now, for those of you who are taking math classes or you like math, vectors are super powerful because we can represent, obviously, a collection of numbers that might represent a row in a matrix. Or maybe if you like physics and you like vectors, right? Three-dimensional vectors or even four-dimensional vectors. So once you understand how to work with a vector, if you like math, it opens up a world of very powerful things we can do. And for sure, with all of this AI stuff that's going on lately, you can be sure that a lot of the data that it is working with is actually kind of coming in a vector, or we'll see later in the course, a two-dimensional vector. You can think of that as a grid kind of data structure. So they are pretty ubiquitous and super, super helpful. But let's look back over our shoulders for a second at what we learned last time. So for loops are just another version of a while loop, and they always break down into three sections separated by semicolons. So those semicolons are kind of weird. Looks like a function, so you might be tempted to put commas in there, but normally we just put in those semicolons. And we initialize a variable. We have a test condition just like a while loop. While this is true, keep looping. So it's not the other way around. It's like how under what condition will we keep going, like a while loop, and then how do we increment some counter, okay, and then all the work we want to do. So that's the basic structure. And usually what we see over here is this x equals x plus 1 or I equals I plus 1. But keep in mind, if you're just adding 1, you can say x plus plus, or some people like to say plus plus x. They both work the same. And you're either counting up or you're counting down. And so, we can kind of plug all sorts of different variations of that into that increment section. So if we look at a while loop like this, of course, the mapping is pretty straightforward. The initialization section goes here. But keep in mind, as we mentioned last time, now the x only exists within the curly braces. So what we're saying here is, hey, create me an x so that it's only part of this neighborhood, where up here, that x that we had up there in the while loop kind of exists in the scope of this entire area of code here, right? Before and after the while loop. So that's one subtle difference that often really forces a decision of going one way or another, while loop or for loop. The rest of the stuff is otherwise pretty much identical and all on one nice line there. Okay. And in this case, the X is gone right after that curly brace happens when we're in our code. Okay. Now, typical mistakes, just watch for this one. The worst one by far is really that semicolon because it's a silent killer. You do that, you really don't know why your loop isn't working because C++ won't flag an error. So watch out for that one. We really only need them at the end of each statement of code, right? Statement, semicolon, statement, semicolon. Otherwise, it's kind of like an if or a while loop. No semicolon right there. Okay. And then remember that our strings, well, this is going to come in handy today. So when we're working with strings, we said, hey, we can get the dot size with two parentheses. That's called a method. And the string data type supports that method. So we can say string.size. As we saw, we can also say, hey, put a x at location 0. Okay. Or calculate the size minus 1 to find the last addressable position and then shove an M at that location. Okay. So those are our size and at methods. And we also talked, I think, briefly about the pushback. So you can say, hey, I want to glue stuff on the end of the string. So in that sense, the string data type is kind of like that vector train we saw on the first slide, but it only really supports pushing back of a single character. So notice this has single quotes, right? This has double quotes. This is a string. This is a character. We can only add individual characters to a string with that pushback. So some people try to push back a whole word on there, and string says, no, I only do one letter at a time. Okay. So there are some limits to what we can do with that pushback. Now, if I want to add more stuff, I can use the plus, so I can add one letter, or in this case, I think I could glue on a whole word if I wanted to as well. I have to check and verify that. But those are two different ways of doing the same thing. String.pushback and str equals str plus p. Okay. So we will see that the vector, fortunately, supports these similar methods. So they're different data types, but they support the same methods for sanity's sake. So we as programmers don't need to memorize a different set of rules for every different kind of data type. So that's a very nice piece of design that somebody did for us. Okay. Now, watch out for this error just before I leave this page here. str equals str.pushback. I think I got this wrong the other day. I was staring right at it. I couldn't figure out what I'd done wrong. But basically, str doesn't return anything. So there's nothing that we need to get back from the str. So when you say str equals str pushback, you are, if you're not creating an outright error, you might be corrupting your data. So we really only just need to say, hey, modify yourself in place, object-oriented kind of operation. So str is the object, and the operation is, of course, the pushback. So we don't need that str equals str.pushback in that situation. Okay, so reversing a string, we talked last time about really just a technique. There's nothing particular about this except the code that gets it done. It's the steps that are important. And so the idea was, hey, I could put X at the end and then just say temp.pushback what's at X and then move X over time. And that moving of the X happens, of course, in a loop. And then we're just sort of pulling from that area and then, or copying and pasting it onto the end of that temp string. So that is one algorithm for, reversing a string of any size, which is really nice to be able to do. Okay. The in-place one, which is just trickier, but gets to the heart. If you like puzzles and you consider taking Comp 220 in the fall, we will do all sorts of interesting and famous puzzles. One of them is, can I swap this in place without really having a whole extra copy of the string? And as long as I have one single character, like a little teeny tiny scratch pad, I can get the job done by just, copying one thing over. And although I'm not really making this blank, I know I've at least backed up that 0 position. So now I can copy over it, and then I can put the temp and the final position. So every swap in computer science in memory requires 3 things: the 2 locations we're swapping and a little teeny tiny scratch pad. Okay. So that's the slightly harder version. And of course, we're calculating where the end position is based on X. So again, if you like math, as X increases, we calculate the mirror opposite position of that by just saying string size -1 minus X. So of course, as X grows, this brown arrow moves to the left. So a little trickier, but somewhere we're going to meet in the middle, right? And our job is done, right? We've finished swapping. We don't need to, these arrows don't need to cross over each other. We just stop at the halfway point and that reverse is done. Okay. So two ways to do that. There's lots of other ways out there, but these are what we call algorithms. And we'll study a few of them in this class, but mostly Comp 220 is about studying the truly famous algorithms. So this is our vocabulary so far, all the good stuff. We've seen while, break, continue. We're going to add the vector. We saw the for also, so I don't have that over there right now. We're going to add vector less than some type. Now, what goes in there? Anything goes in there. Any of these can be the things that we're collecting. Sorry, not the void, but I could be collecting strings, doubles, floats, characters, integers, or booleans. So that vector kind of train can carry any single data type that we choose from up here. And so that's what we're really doing inside of those less than and greater than symbols. And we'll look at that in detail here in just a second. Now, let's take a look at clock for a day one time before we go on. So what we want to produce with our assignment that's due in 1.5 weeks is this list. And you can kind of have fun with this. There are so many different creative ways to produce this list with what we've already learned in class. But there are a couple things that might save you some time. So how many minutes in a day? Pretty easy to calculate. It's the minutes per hour times the hours per day. Of course, that's 24 times 60. That's going to give you a number, and that's all the way from 0 to the last minute of the day. So the first minute of the day starts at 0. So 0 minute for the current minute, let's say, and ends at, hours per day times minutes per hour. But we can calculate noon by just sort of dividing the minutes per day by 2. So if you've got a for loop that's counting from 0 up to this number right here, then you can easily spot when you've kind of come up on noon, because mathematically you just divide that number by 2. And it's like, aha, I'll just write the word noon there. Okay. So this is really just a for loop where we're going through and potentially just counting by fives. So we go until we reach the last minute of the day, and our increment for our for loop can be 5, right? So we're at 0, then we're at 5, then we're at 10, then we're at 15. You might think, okay, how do I turn that into hours and minutes? And that's really kind of the fun part of the program. It's like, okay, I know I'm at current minute 5. So what would that mean? Okay, well, we can use our friend modulo for figuring out those answers. So whatever the current minute is, modulo 60 is going to give us the minutes in the hour. Okay, so if we were to just go through a loop and print out the modulo of whatever this was by 60, we're kind of going to get the minutes. Okay. And the other hint is if you divide as an integer division, so divide by 60, you roughly get the hour, but you get it in military time, 0 o'clock, 1 o'clock, 23 o'clock. So that division will get you kind of in the neighborhood of the hour. And if you kind of think about it that way, then we're really just doing a for loop, starting from some minute, right? We're assigning it to some current minute variable. We continue while it's less than the total number of minutes of the day, increment by 5, right? That's our kind of pseudocode for loop. And the first and easiest one to do is deal with the easy ones, right? If the current minute is equivalent to midnight, right? Midnight is going to be 1440, then we just print midnight. Else if, kind of see where we're going with this, a logic chain. Else if we're equivalent to 720, right? Then we print noon. And now you've started chopping the problem down. It's like, oh, but then if it's less than noon, I know that I will probably be adding on an AM over here, right? And if it's greater than noon, I'm going to be adding on a PM. So the name of the game is really just thinking about your logic chain and breaking the problem down and throwing in a little bit of, math. So remember that modulo 60 gives us a remainder, okay? So that's going to be the minutes side of the equation, right? And dividing integer by 60, right? An integer data type divided by 60 is roughly going to give us the hour over here, okay? Now, there are multiple other ways. Some people like to do a double for loop, which we haven't officially covered in class yet. But for those of you who want to challenge yourself, that's a harder way, but kind of maybe more like you think about a clock. You think about an inner loop going around really fast for the minutes and an outer loop going around more slowly for the hours. It's still kind of tricky, but if you like, that kind of thing and you feel like you need a little bit of a challenge, then think about that. You can kind of do the double loop. And there are good hints in Canvas. So don't forget to look at Canvas and the README file for this, for those of you who are working in Program IZ Pro, okay? So all that stuff should be up there. So I think those are the main things. You got to use a for loop, no while loops there. But let me see if anybody has any questions before we kind of press on from here. Okay, good. So you got a week and a half on that. So not too long. All right, global variables. What is a global variable? Well, remember that we said curly braces create a neighborhood. And so when we create a variable, it lives most naturally inside of its local neighborhood. So things inside of functions live inside of their neighborhood. Things inside of while loops live inside of their neighborhood. But yes, there is this area, this void space in between. We call it at file scope. If you drop something in these areas here, you are creating a variable that everyone can see and accidentally use. So for example, if I put int num equals 10 there, and then I have an int num equals 11 here, and then I print num, you might think, oh, which one am I actually going to print there? Am I going to print the 10 or the 11? Well, C++ does have rules where it thinks locally, right? So if that phrase, think locally, or maybe think globally, act locally, but code is the other way around, thinks locally. So it's going to print this one here, but you can see how that's confusing. Because if you didn't see this, you missed it because you had a really, really long main function. You might think, oh, it's going to be 10, and you'd be surprised when it comes out as 11. So this is one of the reasons why these global variables are frowned upon. Also, let's say you and I both are writing functions that use the variable num, but you didn't know that I put this in there. Okay. So you might think, oh, I'll just use that while your friend is maybe over here using some other variable num. And you can see how when you work on a team, it could get confusing very quickly. So that's why global variables are frowned upon. So, and we tried to reinforce that a little bit in our rock, paper, shears. We said, don't try to calculate the score inside of the who wins turn, because that would be an example of using a variable that probably you would have had to create globally, right? Better to return something back from our function and then use that information to calculate who wins. And that's kind of what we were doing. Okay. So most people say when you're starting out, keep away from these, no-go areas. And although you might feel a little bit constrained, you find that ultimately it's more elegant and easier to track down your bugs. Okay. So, and I'll show you a few examples how we get around that problem. Some of you probably were like, yeah, this is a real pain, but usually we find that if we do it, then, things work out more cleanly. So how do we do it? We usually pass things into a function and get things back. So we talk to the function entirely through its arguments, or sometimes we call that its function signature. It's like, oh, I need to give you things and you're going to give me things back. That's really the A++ right answer in most coding situations. So yeah, we kind of need to restructure things a little bit to get around this constraint, but ultimately that's a better thing. So the way we did it, we said, hey, if who wins turn is equal to computer, then we increment the computer score, or if it's, the computer score is already equal to 4, then we know game's over. So there's whole lots of ways to sort of, calculate that. But that's how we got around that problem. Okay. So just a little bit of words of advice there. I'll remind you of that as we go on. Let's move on then to the vector data type. So this one's fun. So it's really a lot like a collection of things. So I could have a collection of numbers, or I could have a collection of strings. So what you're seeing here is a collection of strings where each string oddly only has one character in it. So in a way, that's really a word with one character. It's not a mathy number that we can actually work with. But we can collect any kinds of things we want. So in the same way we say int I equals 1, or double D equals 2.9, or string str equals a word, we're going to do something very, very similar with vectors. We're going to say vector of type int vi, okay? So that's the variable name, right? Just like these. This is the data type. So this whole mess there is saying the whole data type of VI. What is VI? It's a collection of integers, right? Okay, so 1, 2, 3, 4, 5. So it's like, hey, okay, I'll just collect some integers using this curly brace notation. And these, in fact, are integers in this case. So we can do math on those values. They're not surrounded by double quotes or single quotes. So that's very powerful. Now we have a collection of data. We could calculate the average. We could calculate standard deviation for people who like statistics. So there's all sorts of cool things we can do there. Or we could have decided we want to collect individual characters. In this case, the characters are digits, but they are not mathy digits. They're just character digits. Or collect true and false things. How did you do on your questions on your quiz? Did you get them right or wrong? We could sort of say, oh, we'll collect a vector of true false values to keep track of how maybe somebody did on a questionnaire. Did they get something right or wrong? So the true falses would be in position 0, 1, 2, 3, 4, etc. Always counting from 0. And yes, we could collect words. So an entire dictionary of words, or collection of words in the hundreds of thousands, could be put in one single vector. And we will actually do that for our homework 4 here very soon. Okay. So vector is really a kind of a data type, but it's a custom data type. And so we actually call that a class in most programming languages. So when someone creates their own data type, one of the fundamental ways to do that is create something called a class. And we will absolutely learn about how to do this ourselves. But fortunately, somebody has written the string class for us and has written the vector class for us already. So we'll start using these classes and eventually we will write our own. Okay, so let's look at some actual code. So the first thing we got to do is include the vector library. Always, 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 always. So our first couple of practice problems today, you'll have to do that just to get the mechanics in your brain going. We'll use our using namespace std because vectors require an std double colon, just like cout, unless we do this thing right here. So we'll do that, keep things simple. And again, the format is just vector less than, choose your data type, right? So that's the type of our variable. That's the name of our variable. And then this is kind of the subtype. What are the things that we're collecting? And here's my initial values. And they have to match this type in here. So if this is integer over here, then these better be that exact same data type. Okay, 1, 2, 3, 4, etc. If I said Boolean, they better be true false values, no quotes. If I said char, single quotes. If I said string, double quotes, always separated by commas, etc. Okay. So that's going to be our syntax. So keep in mind when you're dealing with vectors, we got to say the type. That's all just the type. And then we give it a name. Fortunately, they have the same methods that exist for string. So if I have a bunch of integers, and I call this vi because it's a vector of integers, just helps me remember, I can check its size, okay, see how many things are there. I can see what's at a particular location. I can jump to the, a particular position or calculate a particular position. So vi.size -1, right? So if I've got 9 things, then the -1 is the 8th position. 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So that's the last position right there. Okay, so we'll do that quite often, just so we can calculate it directly. And we can do pushbacks. So we can add something to the end, and now the size has gone up, and we can go a little bit further if we're going to print those out or change those values. So we always want to check the size of a vector before we go probing through its contents by using that dot size. Even if we think we know what it is, it's better to use the dot size just to be safe. Okay? Otherwise, we will certainly crash. Here's the same thing with strings. So if I want to collect some words in a string, 2 of them or 2,000 of them, really doesn't matter, just like that. Now, the other nice thing about the initialization is I can kind of spread it out across multiple lines. So I can notice I've just sort of taken this thing here, of course, moved it down to here, and we just got to figure out what's separated by commas here. And putting them on separate lines is sometimes useful because people like to explain what this is all about. This is the peach. I'm going to use it for this. This is something else. So you can do this any way you like. C++ is going to search until it gets to the semicolon. And it's going to expect you to put something like that around comma-separated items if you're going to initialize it. Okay? If you don't initialize it, it's like that empty train, right? It's there. It's waiting for the cars to be added to it. Okay? But in this case, we're kind of initializing it with stuff to start. Here's another integer example. Right, we have even numbers. Here we have odd numbers. We put those on separate lines. Same thing as far as the compiler is concerned. It just has 2 vectors there. Okay, so let's kind of do a little print because one of the things, unfortunately, that we don't get for free is the ability to do cout of an entire vector. We have to print it ourselves. So let's create an integer of type, or vector of type integer, give it some values. And I just threw out 21 through 30 here. If you want, you can choose some different values if you like. Then let's write a for loop, kind of shake the dust off of our lesson from earlier in the week, and use the size to determine how far you should loop, and use the at to print out a particular value. And it should print out what you initialized, in your code. So let me jump in here and we can do this together. This is a really good one to warm up on because, we don't have a lot of experience so far with the for loop. So first things first, we got to include the vector library. It didn't come for free in the base language. It's something somebody wrote and it became famous, you could say. And so now it's just out there for us. And then we will create the vector. So vector int, and I'll just call it VI. You can call it whatever you want. Equals, pair of curly braces, and a semicolon. And I'll just create some values. What do we say? 21, 22, 23, 24, 25, 26, 27, 28. And I'm going to just stop right there. Okay. And then I'll do my for loop. So how do we do a for loop? For. Okay. And we got three parts, right? So the first part creates the index. So int, I'll just say x equals 0 for the 0 position. Continue while x is less than vi.size. And don't forget your parentheses there. Okay. So notice I used less than size. Sorry, this is so small on the screen. Let me zoom up on this a little bit for you. Okay. So you can kind of see that I'm using size with parentheses on it, and then I'm going to say x plus plus. Okay. And then if I want to print something out, I'll just kind of do this on its own line here. I'll say cout vi dot at position x, and I'll glue on a little comma there. And notice I skipped the curly braces this time. I get one free thing that glues itself to the for loop. And so that means my for loop is done now. That's the end of that for loop right after that. So basically I can just say, hey, end that line with an ENDL. Okay. So this is really part of this. And if I, get rid of all my kind of annoying comments there, you can kind of see that's the for loop. And like we've seen before, C++ does not care. You could even put that all in the same line if you wanted to, okay? But I'm going to put it on its own line by itself. Tab that in, okay, for clarity. Okay, so let's see if it actually runs. If I missed anything. Got it. Okay, there we go. So we unfortunately need to do something like this every time we want to print out a vector. It'd be really great if we could just say cout vi, but cout kind of doesn't know how to print out a vi by default, or our vector by default. So that's what we're kind of stuck with. Okay. But now the world has opened up to us hugely because, coding is so much more fun when you have data, and there's lots of fascinating data out there to be grabbed and processed. So, but putting it inside a vector is kind of our first step. Now, let's just try to print this in reverse. For those of you who like a little extra challenge, if you got your code up, switch your for loop around to be I equals vi dot size minus 1. That's our last position. Continue while I is greater than or equal to 0, because we also have something at position 0, and decrement your I here. Same vector, just different iteration sequence, counting backwards rather than counting forward. And you should see all of your values get printed out there, just in reverse order. Oops, give you another moment on that. That's an important skill. We are going to have to think forward and backward with our for loops. And it's tricky because here we're adding the equal sign, but if we're counting up, we're not going to count up until we're equal to size. We're going to count up only while we're less than size. So they are kind of confusing. It's like, wait, which one do we do when? And the key is just to think, we start counting from 0. We always have the last position that's 1 minus the size, or size minus 1. Okay. Now, vectors can push back, which means we can collect data dynamically from somebody at the keyboard. So we can start to write useful tools now that collect data and maybe calculate an average temperature or calculate a standard deviation based on interactively entered data. So we start with maybe a blank vector, right? And then we have a number and we ask a user to say, hey, give me an integer, collect it, and then push it back. So this is just getting one, but we could put that inside of a loop, kind of like we did, for rock, paper, shears, or even use a for loop in this case. And now we have a very useful way of collecting data. Okay. And unfortunately, we can't, do that. We got to actually write that for loop for printing out the data as well. And that's what we're going to do, right? So that right there would cause us an error. So we're going to have to write that. So let's collect this time and print numbers. So we're going to define a vector. You can call it my numbers or VI if you like. And then we're going to ask the user, how many times do you want to go around? So this is for us to fill up the data. So if this is a scientist entering data, our program says, hey, how many numbers you got? Loop count. That's the first variable we get from our scientist. And we use that for the loop where we do the pushback. So our for loop would go from 0 to less than loop count. That would give us an opportunity to collect loop count numbers. And then we would do our cin, put it in a temporary value, push it to the back. And when we're done, after we've collected the correct number of values, we can have a second loop where we print that out. Okay, so let's do that one together. And just remember, we want to use the dot size. So we're going to kind of wrap this up here pretty quick once we get through this. But don't forget, we need our vector library. So pound include vector. Okay, I know it's a nuisance, but kind of got to do it. Very often when we forget that, the compiler gives us some very confusing response. It doesn't really say, hey, you forgot the vector library. It says, I don't know what vector is, basically. So let's go down here. So we want to ask the user, first we want to define an empty vector of type integer. So I think we're assuming it's going to be called my numbers down below. So I'll just go with that. So vector int my numbers, and it's going to be empty. Okay, so it's kind of like int x. It's got nothing in it. How many integers would you like, right? So we ask the user, we collect that value from the user, and now we're going to put that value in our for loop. So we're going to go from 0, continue while I is less than loop count. Now, many of us, including me, on a slow morning would be like, I'll just put in my numbers.size, right? My numbers.size, right? Why wouldn't I do that, right? It's tempting because it's like, hey, professor said I need to do that. But guess what? Our size is 0. So if we're collecting the data and we put my numbers.size, we're not going to collect any data, right? So our vector doesn't have anything in it. So the user is telling us loop count, okay? Loop count, please go around loop count times, increment this value. And what are we doing? We ask them for an integer. We put that in a temporary variable first. And I have one up here called temp number. And then we can push it back. I can say my numbers dot push back temp number. So now we've collected the value. So this is our data collection loop. And once we have collected that many numbers, okay, so 0 to less than loop count is loop count loops. 0 to less than or equal to loop count would be loop count plus 1 loops. So not super critical, but if you find you're getting too many data items in your vector, you might have put an equal sign there. And then we got to print it out. So how are we going to print this out? Same game, int x equals 0. This time, it's probably best practice to continue while x is less than my numbers.size. And you might say, why? Well, maybe there's like 1,000 lines of blank code in between there and here. And who knows? Maybe somebody changed loop count, right? Maybe loop count is no longer what it was. It's best to trust the vector at telling you what size it is when you're trying to print out the vector. Right? So we say, hey, we'll go while we're less than your size, and we'll print out what's at location X. Okay. And we'll do that over and over and over again. And finally, we'll do that ENDL there. So let's try this real quick. So how many integers? Let's say 4, and I'll just make it simple. 1, 2, 3, 4. And there's our 4 integers. So that was pretty quick, but you can imagine we might do all sorts of, interesting statistics with the data that we collected there. And we just sort of, printed them back out again. Okay. Let me get all this. I'll get you back to the actual, summary of the code there. Okay. So this is where the comments start to help a little bit, right? So here is where we collect the loop count from the user. Here's where we load the data from the user. And here's where we print out what the user gave us. So those ending curly braces or any kind of comments around there start to really help us keep track of where we're doing what in our code, right? Questions on that one? Everybody okay? All right, let's see if we can build on that now. So we put all of that code in main, but sometimes, we want to print a vector over and over and over again. So we don't have to write that silly for loop 1,000 times. We want to put it in a function and just call the function so we have less code. So we often say never write the same code twice. Okay, so this kind of thing right here becomes very tedious. You're like, okay, we're writing that again. And very often that's just exactly how it is. All we end up doing is swapping out the I for an X or the V for another variable, but that ends up being something we do quite a bit. So we should really put that in a function, call the function. So how would we actually define that function? Well, we have functions have names, they have arguments, right? So there's an argument name, and they have an argument type. So in this case, of course, our argument type is just going to be that, vector int. Okay. So that's the type of data that's coming through the doorway. We really only have one doorway. It just so happens it's sort of an accordion doorway. It can get bigger and bigger and bigger. We can pass through a lot of data through that argument. And in this particular case, it's a void function because we're just printing them on the board, on the whiteboard, so to speak. So it's not much more complicated than our normal function. But you can imagine all the cool things we could do. We could write a sort words function where somebody gives us words that's a vector of strings, and we write a function that goes through and puts them in alphabetical order and returns a brand new sorted string. So it makes a copy, puts it in order, gives it back to us. So this is a function that returns a vector in addition to receiving a vector. And so homework 4, we're going to do a few of those kinds of functions to get us all in the right space. But definitely vectors and functions together allow us to do some really, really, really powerful things. Okay, but we, of course, have to write those functions. Okay. So that's really what we're going to do. And by default, when we pour something into this argument, we're basically pouring in a copy. So if imagine someone knocked on our door and said, hey, I have a package for Professor Yates. I open the door, I receive the package. I'm essentially receiving a copy of the package, and they walk away with their own copy. So if I open up the package and it's got numbers in it and I change the numbers, I haven't changed the numbers out in the hallway. I've just changed them inside of the function. So keep that in mind. By default, in C++, when someone gives us an argument, we're getting a copy of that thing. And whatever we do to that is kind of private to our function unless we return it or print it on the board or something. Okay? So we'll see some examples of that. But people say C++ is a copy-centric language because by default, very often it's like, hey, here's your copy, here's your copy. It's throwing copies around all over the place. So let's do that with our print function. Let's just say void print vector is going to be our function call to write on the board, so to speak, and we're receiving a vector of type integers. So let's go in and take a look at this code. We're just going to do a quick modification. do that. I think I probably just have to do a few edits. I'm going to put my vector library here again. But this is what we call refactoring. So when we're writing software in C++, and we want a prototype for our function here. So it's a void function. It's going to be called print vector, vector. Okay, it is going to receive a vector int, and you can call it whatever you want. I'm going to call it numbers, right? So that's the name of the argument. That's my prototype. So I can copy that down below and start my function. Okay, but instead of the semicolon, we need some curly braces. Okay, so there's our curly braces. And the code is right here waiting for me. So refactoring is kind of, you do that head scratch and you're like, man, I just need this to be a function. So I'm going to cut it out of there. I'm going to move it down to here, clean things up a little bit. But notice we have a small problem. I'm calling my vector numbers, but that code I took from main was calling it my numbers. So we're going to change this code so it's using the name that we have agreed to use inside of our function, which is numbers. Okay, so that's an important change. Very often we copy and paste code into our functions and we don't take those things into consideration. So that's all I got to do. That's my for loop. Ending cout, end of function. All right, so now how do I call the function? So let's go review what we're doing inside of here. We ask the user for a loop count. We've done this, right? For I equals 0 to less than loop count, please give me a number. I want to do common input, cin into the temp. I think we call it a temp number. Okay, so kind of made you write that twice, temp number. Push back the temp number onto my numbers. So we are indeed working with my numbers here, right? This is main. It has my numbers. We're building that up. And then to call the function, what do? We just say the function name, print vector my numbers. I don't need to put in all of that vectory stuff right here, right? That is only needed when we define the prototype, right? Here. And when we implement its matching function down here. When we call it, we just pour it in there. It's like, hey, here's your numbers, and it gets printed. Let's see if I got any bugs here. How many would I like? I'm going to go with 4 again. 4, 3, 2, 1. Okay, and it prints it for me. And the nice thing is I can, I can print it as many times as I like, right? And we'll see that that's a very useful function to have. 1, 2, 3, 4, 5. There we go. Okay, so don't let the extra syntax throw you too much. It's really just about getting the function written, and calling it is kind of pleasant. It makes your job easier once you've done the initial work. Okay, so there's our print. All right, and there's our call right there. So there's loop count, load, nice and simple. Keeps our main section a little cleaner. Okay. So when we develop code, this happens a lot. We're just like, we're in a hurry, we write a lot of code, then we take a breath and we go, I should put that in a function. That'd be so much nicer. It's a little bit of work, but then it makes my main section a lot nicer. And again, we call that refactoring. You look at our code and go, I could do better. Okay. Now, you want to implement your functions at the bottom after main. So when I often say after main, I'm probably not always clear enough. It's after the matching curly brace of main. So we got to find the main, and then we can put our function down there. Okay. In case that's unclear. Now, we can imagine all sorts of pretty cool functions. So if you think of your math classes, statistics, and these things you'd have to do on your calculator, we could write some very cool functions to do this. We could say, hey, I want a function that receives a vector, makes a copy of it, multiplies everything by 2, and then sends it back. Okay. So what can I do with that? So here's my kind of for I equals 0 to size, right? And I can change the vector locally inside of here, right? vector at I equals vector at I times 2. So notice what I'm doing there. I'm saying pull out what's at I, multiply it by 2, and put it back in the same location. That's pretty cool. So we're still just changing a copy, which means then we must return that copy. It's like, hey, here's your modified copy. So that goes out the return door here, right? Back to whoever was calling it in the main section. So there is all sorts of really useful statistics and math functions we could write that operate on a collection of these values. Indeed, many people write those kind of functions. Okay. If we forget to do this, C++ will usually flag an error, but not always. And then things get really spooky really fast. So we got to be really careful that we do return that value at the end there. That's an important part of what we need to do. Okay. Now, here's a couple other examples. If I had something with some numbers, right? And then I had something that has nothing in it yet, I can say more nums equal double each nums. So if we think about that double each thing we wrote on the previous page, it just works, right? It's like, hey, here's an integer coming in, right? And I get a copy and I write it on top of that. So now suddenly this is going to have 2, 4, 6, 8, 10, right? If this was 1, 2, 3, 4, 5, we know if we call our print function, we'll see 2, 4, 6, 8, 10. Okay. We have not yet changed this one. This one is still 1, 2, 3, 4, 5 because we just got a copy of it, changed it, and then returned it for that. Now what we're doing in this case is we're saying, hey, I want to take 2, 4, 6, 8, 10, double it, and then overwrite 2, 4, 6, 8, 10 with the doubled result. And that's okay too. It's like saying, hey, you were this, now give me back something and overwrite the previous version of that. And that's okay, because those are copies. And we could go on and on. The other thing we can do that's really nice, notice here what I'm doing. I'm actually creating a vector on the fly. So I'm saying, hey, here's your vector 2, 2, 2, 2, 2, just like when we initialized it up here. And C++ says, oh, I'll turn that into a vector and I'll give you back something you can overwrite, right? That's double. So you should get the 4s from that. So hopefully this kind of demystifies the difference between creating the function and calling it, right? Here we're calling it, right? Here we're calling it, and getting something back, right? And our prototype is on the other page there. Now, some of these things that return other examples, these are just other examples. Pass in a vector, add 1, give me the vector back, okay? Or pass in a vector, this is the same we just saw, multiply it times 2. That's by definition what we're going to do. Or more mathy, if you like, multiplying the corresponding vector elements of this times the corresponding elements of that and returning the result. That is a very useful kind of vector function in math or physics. We want to multiply the 0th value here times the 0th value here. And all of those things would happen inside of a while loop. Adding two vectors together, here again, very useful in math, physics. Add the 0 position to the 0 position, create a brand new vector and give that back to me. Okay. So in each of these cases, we're returning a vector. So we would say vi equals add 1 to vi. Okay, that gave me back a vector with 2, 3, 4, 5, 6, and it overwrote what was here. So this is now gone, and we have this instead, right? Or vi equals the sum of the vector with itself. That's okay. So it's just going to take whatever it was, add it to itself, right? Send a copy in here, send a copy in there, send back a copy, and overwrite. Okay, so now we have 4, 6, 8, 10, 12. Okay. Now, the vector type that we're using here is got to be integer. If I try to cram something in there that's not an integer and I don't have a matching function for it, then we're going to have a problem. So if I did this, VD, and then I did a VI, and I tried to say some vectors VI and VD, C++ goes looking through here and it's like, I have a sum vectors, but it's an int. It's not an int double. And so good old C++ is going to throw a flag and say, I can't do that. I don't have a function that matches the prototype for that. So that would cause an error unless, because that's a double, right? But unless you write another flavor of the function, you might be like, what? I got to write two of these things? Yeah, for the moment, yes. So you literally have to write one that looks almost identical, except for that one thing. And even though the guts inside of your function might be identical, the prototype or the argument types have to match however you're planning on calling it down here, or it generally won't work. Okay. So it's like, oh gosh, that could be a lot of flavors of that sum vectors function. And that's true. You might have to write 3 or 4 of them. Kind of depends. But this is the name of the game, right? So let's write one of these. We're just going to, we call it scaling, but we're going to multiply an entire vector of doubles by a single number that somebody gives us as an argument. So it's a pretty useful function. We call it a scale function. So we'll say, hey, here's my vector, copy of that. Here's what I want you to multiply it by. Give me back a new vector. Okay. And then we'll call our print vector function. So that's what we really want after here. We should be able to get that working pretty quick. Let's just dive in and have a look at the code. Yeah, I think we're going to be done with plenty of time today. So let's just jump in. Let me check. Just kind of getting everybody in the habit here. Vector library. Okay. There's our print vector prototype. There's our scale vector prototype. This one's already written for us. We have to write this one down below. Okay. So we're going to need that scale vector. I'm not even going to look at main. I'm going to go straight to my job for the day. I'm going to go down here and say, oh, okay, I got to write this thing. Oh, well, what does it need to do? Well, I need some curly braces, right? Okay. I'm going to need a loop where I go through that thing and multiply each value by that and put it back and then return it. Okay. So let's just do that. For int x equals 0. And you can use x or I. Sometimes I switch back and forth, so careful for that. While x is less than what? Vd dot size, right? X plus plus. And I'm going to use some curly braces here, but you don't have to. And I'm going to say, Vd at location x should receive the value from Vd dot at location x times none. Notice that I just said equal to, not less than or equal to. All right, sorry, I said less than, not less than or equal to. And then crucially, we have to return what? Vd. So we're saying, hey, I modified this in my own little area here. Now I got to give you a copy back at the end of the function. Okay. So now let's go see where we need to call that. Okay. So it shouldn't be too bad. I think most of this is written for us. This one is already fully written. So all we're really doing is we have a call to the function, right? We collect the numbers, we multiply each of them by 0.5, we get that back, and then we just want to call the function to print the vector, right? My numbers. Okay. So if we do this right, we should get something that kind of makes sense. If I don't have any bugs, my numbers. I forgot to declare that, didn't I? Double my numbers. Oh, guess what? Haha, I got caught in my own trap. Guess what? Print vector only knows how to print what? Integers. Yeah, so we got to change that to double. So change that to double. And then we have to go change our prototype to double as well to make C++ happy. Or we could have copied and pasted and had 2 of those flavors, right? And of course, I forgot my semicolon because I formed bad habits using Python, or Pythonic habits, I'll just say. Okay, how many 4 values? I'm going to call it 2, 2, 4, 6, 8. Okay. And when we multiply that vector times 0.5, right, that cuts everything in half. So that, of course, 2 becomes a 1, 4 comes 2, etc. So we want to design software that has all these cool little atomic functions that we can build upon and build higher and higher mountains that do amazing things. And we get stuff like self-driving cars and ChatGPT and stuff. Okay. So we got to start at the bottom, or somebody does, right? So there's our kind of somewhat intimidating main, collect the loop count, load the data, call the scale function. So now all that mess is neatly tucked away inside of this scale vector thing, as well as the print vector. So we could even really probably put this in a function too, right? Imagine if we just had a function that just collected a certain number of values and gave us back a vector. That would be another great function to write, and that would make main even cleaner. And again, we call that refactoring. That would be a nice refactor. And there's our kind of changing over to the double. It's really all we need to do. And yeah, you could have two exactly same named functions that only differ in terms of the type of their argument, and they can live together happily. They can both be in your code. So for example, I could go over here and say, seems like a waste, but I could write that with an int here, right? Int and then I need to have also a prototype for that up here. Right, so now I have two flavors. And many of you are probably like, seems to me like we're writing duplicate code. And you would be right. And we will learn in this class how you avoid that problem. But that's kind of what we sort of need to do if we want to have all variations of that print function. Oh, sorry, I thought I was doing my print function there. Sorry. So I duplicated my scale vectors one. Anyway, hopefully you get the point on that one. That's kind of high level how we got to kind of cover all of our bases there. And there's our scale vector function. So important to return that. If you don't return that, all things start to break. Okay, couple things before we move on. What's wrong with this code? So here's a prototype, scale vector. We need a double. We're going to multiply by a double. And we might say, okay, what's wrong in main here? So I have a vector of numbers, 1, 2, 3, 4, 5, and I say scale vector. My number is 20. And you could look at that all day long. And when you print out your vector, it's still going to print out 1, 2, 3, 4, 5. And your code doesn't complain. The compiler's happy. What is going on there? Well, what's happening is, notice that our vector is giving us back the answer, right? Our scale vector function. It's giving us back something. So this is that bad joke about a tree falling in the woods when no one's there. So here comes the return value, and there's no one to receive it. There's no variable saying, x equals scale vector. So if you don't give that, C++ just silently assumes you know what you're doing, and we never hear about it. So we got to actually put an equal sign with a variable, like my numbers equals scale vector my numbers, something like that. Otherwise, looks like our code's working, but it's just not doing anything because we're ignoring what came back. And I will trip up on that too myself. So it just kind of happens from time to time. We got to look at our function and remember it's giving us an answer back, and we want to put that somewhere.
And so the minute it goes on to the next line, that's completely gone.
So exactly.
You couldn't even cheat and say, I'm going to do a print statement afterwards. As soon as the line goes, next line, it's evaporated.
Yes, exactly. And that's a great point too. We often think, oh, I did it. It's somehow there. And in truth, it probably is somewhere in memory, but we didn't attach it to anything, so we can't get it back. So sometimes putting something in a variable name is really just so we can hang on to it. We don't lose it. You did all the work. You just didn't capture what you got back from your function. Now, other cool thing is we can collect words. So a vector of string is words, right? And I like to call it words, but it really could be sentences. They're not necessarily just words. They could be long sentences, but the vector is going to collect them And so we could ask a user, hey, give me a word. I'll put it in temp, and then I will push it back onto the end of the words vector. So a lot of board games and card games, this like opens up a door to like, hey, we can play Scrabble, we can collect letters, we can collect words, we can play Wordle. I don't know if anybody's ever played the New York Times Wordle game that was so crazy popular during the pandemic. We can totally write that program with this kind of collection of words, and it's a whole lot of fun. Okay, so we're gonna try that just to see what that's like, and we'll go through that loop a few times, and then we'll print them out, right? Or we can do all sorts of other things with them. So let's read words from the user. So we'll call a variable one word or word if you like, but one word makes it really clear. That's just one word. These are many words. Okay, and those are nice titles to use for our variables because they tell us what we're trying to accomplish there. Okay? So let's take a look at how we might kind of modify this very similar pattern. Again, let's look for including the vector. So pound include vector, include vector. And to be properly correct, we should also include string. Okay? A lot of times it gets included for free, but technically speaking, we need to include string as a library in our code. Now we're kind of ready. So what do we want to do? So we want to declare a temporary variable of type string that we can use. Okay, so let's say string one word. Okay, all right. Declare the vector that we're going to put them in. Vector of type string words. Okay, it's got nothing in it yet. Then we're going to say while true, just get an infinite loop going here. Give it a curly brace, end my kind of while loop down here. And then I want to ask the user for a word. Okay, so see out, give me a word. Cin, and we'll put that in one word. So we're just holding on to that temporarily. And we can add a nice feature like rock, paper, shears here. We can say if one word is equivalent to quit, then break. Okay, and you can put that on the same line, or you can put it on the next line if you want. We're going to break out of the nearest while loop. So that means we'll end up down here. Okay. Otherwise, let's collect that word. So we'll say words dot push back one word. Okay. So now we have a copy of that. So we'll go around and around and around until the user says quit. And then we want to print these things out. Now we're not going to write that whole print function again, but we are going to do a super fast for loop. Int x equals 0, continue while x is less than words dot size, right? And then x plus plus, curly braces, okay? See out words at position x. Oops, forgot my little connector there. NDL. Actually, I'll just say comma. Comma. There we go. And I will end. I always like to end with an ENDL. So we go to the next line. So let's just see if that works. Okay, so I'll say apple, peach, banana, orange. Quit. There we go. So homework 4, we're going to be doing this kind of thing, but we're going to have a dictionary of 170,000 words. So it really actually is the Wordle dictionary, or more than the Wordle dictionary by a lot. But it gives us a lot of flexibility. We could create all sorts of fun, small word games, or if you like me, like cheating on the New York Times puzzle weekly question. I usually, when I hear it, I go write some code and figure out the answer pretty quick. If you have a dictionary, you can do a lot of really good stuff. But this is really that program at a kind of high level view. Libraries, loading, printing. Okay. And of course, we could move that printing code into a function. We could even put the loading part into a function if we wanted to clean up our main area even more. Now, what if if it's like Wordle and we're just using 5-letter words? I don't know if you guys know that, but maybe we're like, hey, we're only taking 5-letter words here. So a nice thing we could do, if you remember that our continue is like the shortcut to do-over up top of the loop, we say if the one word dot size is less than or equal to 5, continue. Otherwise, go back up, or if it's less than or equal to, go back up and do it again. Sorry. Otherwise, we collect the word. So if this isn't exactly Wordle, I should say if the one word is not equal to 5, then that would be a Wordle rule, but you can change that logic in any way you want. So we might call this a filter in data science. We'd be like, okay, you gave me a value there that's not in a very logical range, so I'm going to call you on that and send you back around and let you try to input that thing again. And hopefully that feels familiar. Some of you might have used that for your rock, paper, shears logic. Okay, so that is our kind of last one there. That sets us up for our lab today, which is really just about implementing a function. It's a little bit different than what we got. We're going to have this function create the entire vector kind of from scratch. So we're going to say, hey, I'm going to give you a number called an argument, and you're going to create a vector that goes from 1, 2, 3, 4, 5, 6 up to that number and including that number. And then we're going to print that thing. So most of main has been written. You just have to fill in a few missing pieces and then call your get vector ascending to get back the thing that you returned from your function. And then you're going to print that thing. So if there's going to be a mistake, usually it happens because we do all the work and then we forget to return that thing. So don't forget to return that thing. So if you say 5, then you should get a vector 1, 2, 3, 4, 5. If you say 7, you should get 1, 2, 3, 4, 5, 6, 7, and so on. Okay. That should be what your function creates and returns. Okay. We should be able to do that over and over. So main is going to look like this. Vector int my numbers, int response, we could have called that num if we wanted to. We'll just say, how high do you want to count? Response, call your function, right? Get back the answer, then go ahead and print the answer. So if this is my numbers that you're putting it in, then print my numbers there, right? So that's your main section, okay? And I think there might be one more slide here. Let me see if I got one more for you here. If not, we'll just remember, right? So this is what we're passing into the function. If it's a 5, then we want 1, 2, 3, 4, 5, and we get back the vector. Okay, so we're getting back a vector of type int. And then that goes into our vector down there, right? So if it's that, right, then we need that to go into this function call here, right? Let me just click into that real quick on the previous page. I think it's going to be relatively straightforward from there. Given what we saw today in class, it shouldn't be too big change. Don't forget, got to match your prototype above main, down below. So you're going to have to paste that thing down there, and you're going to have to rewrite your print vector, which I know you already did, but it should be pretty easy for you to implement that, and you can use your code from class today to do that as well. Okay. Final questions? Okay, thanks everybody. Let's go. Have a good weekend, and I will see you on Tuesday. Oh, and if you're still finish up your homework, it's worth doing. Definitely, you want to try to get that in today. You can still get 80% on that today. Okay, thank you.